11.2 Part 2 here. It can be easier to use combinatorics, or the fundamental counting principle, and ways of counting permutations and combinations to find probability rather than listing and counting all the equally likely outcomes. So, finding combinations here. What is the theoretical probability of being dealt exactly 2 sevens in a 5-card hand from a standard 52 card deck? So the things that we're looking for here, guys, is we're looking for exactly 2 sevens. And there's 4, this is 2 sevens, sorry, 2 sevens. Out of 4 sevens that are in the deck. Okay, there's hearts, clubs, diamonds, and spades. Okay, 4 suits, each one has a 7. So we're looking for 2 sevens out of the 4 sevens. We also have to compare the rest of our cards. What's the probability of getting 3 cards out of the other 48 cards? Okay, so all of our cards are accounted for. We have 4 here and 48, which gives us the entire 52. So we're looking for the combined probability of those events, and we know that there's 52 cards in a deck, and we need 5. And then we need 5 cards out of 52. So we want to know what the combinations are there. How many combinations of 2 sevens out of 4 sevens are there? How many combinations of 3 cards are there out of the other 48? And how many combinations of 5 cards out of 52? And I said combinations, not permutations, because the order doesn't matter. It doesn't matter if we get a 7 of hearts and then a 7 of diamonds. Okay, order doesn't matter. We're using combinations. So when we do combinations, the probability of things occurring that we want to occur goes on the top. So what we want or are looking for and total occurrences or options goes on the bottom. Okay, last section we learned about our combination notation, N, C, R, where N is the total and R is the part. Okay, how many of them we need. So for 2 sevens out of 4, we are going to have total 4 options. We want a combination of just 2 of them. For 3 cards out of 48, there's 48 total cards, and we want a combination of just 3 of them. And in our denominator, there's 52 total cards, and we want a combination of any 5 of them. And here we're going to multiply these. Our counting principle says that we multiply the 2 to get our total there. So you can type these in your calculator. We can use the factorial notation, or we can go right into our calculator. Again, it's 4 probability, go over to the NCR button, 2 times 48 probability, go over to the NCR, 3, gives me 103,776 options in my numerator, over in my denominator, divide by 52 probability NCR 5, 2,598,960 total possibilities. So if we were to pick any 5 cards the amount of options are 2,598,960, but the amount that have 2 sevens are only 103,776. So if we simplify that, 103,776 divided by 2598960, we get a probability of like 0.0399, which is 4% chance. About a 4% chance. So about a 4% chance that you can get dealt exactly 2 sevens in a 5-card hand. And that'd be the same as getting 2 aces or getting 2 tens. Okay? It doesn't matter what numbers on them because they're all equally likely. What is the theoretical probability of being dealt all 4 sevens in a 5-card hand? So here we're looking for 4 sevens out of 4 possible. We're looking for 1 extra card out of the remaining 48. And we're still looking for a 5-card hand. Okay, so this is our specifics. And this is our total. 5 cards out of 52. So, total number that we have, total amount we're looking for, times total amount we have, total amount we're looking for, over total amount we have combined with the amount we're looking for. So there's 52 cards and we want any combination of 5. There's 4 cards, we want any combination of 4 here. Here there's 48 cards, we want any combination of 1. So again, we can use what we know about combinations. Here we're going to get just 1. There's 1 option that gives us 7 out of 7. Okay. When we want 1 card out of the rest of the 48, there's 48 options, right? You can get each card once. Over here, I don't remember what we said that was. 2598960. That simplifies if we take 48 divided by that. Two 5,98960. It's approximately 0.000018469, which is about a 0.0018% chance. So a very slim chance that you're going to be dealt 4 of a kind. Okay. Now, finding the geometric probability. A batter's strike zone depends on the height and stance of the batter. Strike zone goes from knees to mid-torso. What is the geometric probability that a baseball thrown at random within the strike zone, as shown in the figure on page 684, will be a high inside strike, which is one of the hardest pitches to hit? So here we're comparing, again, we still want the in theoretical probability of high and inside. We want the occurrences we're looking for. over all options. The only difference here is that we're finding the area, and that's fine. So the particular occurrence is the part in red. It looks like it's 4 inches by 6 inches. So the area there of that little rectangle in red is 4 by 6. The entire strike zone is 17 by 22. So we have 24 over 17 times 2, or sorry, 17 times 22, 374. Which is approximately 0.064, which is a 6.4% chance. So the theoretical probability of a strike being a high and inside strike is 6.4% based off of this particular strike zone and particular high and inside strike part. Now, suppose a batter's, I'm striking out here, strike zone is 15 inches by 20 inches, and the high inside strike zone is 3 inches by 5 inches. What is the probability that a baseball thrown at random within the strike zone will be a high inside strike? So we need the total strike zone and just the high and inside. And that's our probability for high and inside. So high and inside is 3 by 5. The entire strike zone is 15 by 20. We're going to get 15 over 300, which simplifies to 1 out of 20, or 5% chance with the second strike zone. Okay, 5% chance or 0.05 probability. Real quick recap. The probability P of an event is the number such that P is in between 0 and 1, or between 0 and 100%. The probability of an impossible event is 0. Probability of a certain event is 1, or 100%. And there is your assignment.